Hi, welcome to ESI 412, Nanotechnology, Materials, Infrastructure, and Safety. I'm Professor Ukjun Nam at the Pennsylvania State University. So this is the lecture outline for today. We're gonna talk about some of the deposition techniques. So that is physical vapor deposition, chemical vapor deposition, and electrochemical deposition. There are some other techniques other than these three techniques, like spin casting or some other techniques, but we will just discuss based on these kind of three techniques today. And then the second part of today's lecture is we will talk about specifically what kind of deposition techniques are used for the nanoscale fabrication. So deposition or growing is one of the four techniques people are used for the top-down approaches. And then the physical deposition is basically these three techniques are the most popular for the physical vapor deposition. So one is evaporation, the other one is sputtering, and then the third one is a pulsed laser deposition. But all these kind of three techniques basically free some of the targeting atoms from the source materials, and then those kind of source atoms can just fly into the substrate and then do the deposition. So what happens to the substrate is those kind of vapor molecules first fly onto the substrate, and then physically it just land on the substrate, and then it just hopping on and then just move around to find out the right place to settle down, and then finally after the chemisorption this kind of vapor molecules becomes a film. So these are the physisorption, and then this kind of hopping around the surface diffusion, and then the chemisorption is the three major reactions happening on the substrate during the deposition. So thermal evaporator, this is the typical configuration of the thermal evaporator. So there is two electrical posts, and then sometimes there is a shutters installed just right on that source, and then this is the quartz thickness monitor. We're gonna talk about this in the later slide, and then normally people just load the samples on top, and then between these kind of two electrodes people load this kind of boat, or this kind of wire version of the boat, or this kind of flat version of the boat. So basically applying bias between these two electrodes, people just create some kind of resistive heating inside in this kind of boat, and then eventually increase the heating and then melt the source materials, and then just evaporate that. So that's the thermal evaporation is doing. For the E-beam evaporation, it has a filament, so it generates the electrons beams, and then there is a configuration of the magnet. So those kind of generated electron beams kind of bended about 270 degree, and then just landed on the crucible. So this is the example of the crucible. So depends on the material, source material. You can use a metal crucible or carbide or some ceramic crucibles, and then using the electromagnetic field, if this is the crucible from the top, you not only focus the electron beam, but also you can just move these kind of electron beams, something like this. So the basic ideas for move around that kind of electron beam around the crucible is just to consume the source material more evenly instead of just to make a very big cavities in the center. This kind of electron beam evaporation, it has some kind of covers like this. So you can just use this kind of carousel holders or the crucible holders, so you can just deposit multiple different kind of materials at the same time without breaking vacuum. So those kind of materials for the boat, those kind of heater materials are basically made out of this kind of refractory material which has a very high melting point. So at the high temperature, ideally that materials does not make any compound with your source material. So that's the requirement for the heating source and material. And this is the kind of a vapor pressure based on the temperature. So as you can see, all these kind of a different kind of a material has different kind of a vapor pressure at the different kind of a temperature conditions. And then that could be a problems when you deposit compound materials using evaporation. Depends on the material. Some kind of a compound evaporate as a compound. So in this case of that, there's no problems kind of matching the stoichiometry of your deposited film. But most of the cases, if you have two elements of the compound, one of the element always have a lower melting point, and then because of that, when you heat it up, these compound materials, one of the element is kind of a vapor pressure is kind of a dominant than the other, because one element is melting point is much lower, and then as it is melted down, it is dissociated. So that's the problem. So for those kind of materials, to have the to match the stoichiometry, the only way is using a separate source, power source, just to do the co-evaporation. So we can use a different kind of temperature. So if we want to have a one-to-one stoichiometry, we just try to this kind of evaporation rate to be a one-to-one. So using that way, we can make a compound deposition using the evaporation techniques. So for the evaporation, just directly compare thermal and E-beam evaporation. The thermal evaporation has a relatively low purity film, and then it has a limitation in materials because there is a limitation. People can increase the temperature using this kind of resistive heating. But E-beam evaporation offers kind of a much wider selection in terms of the materials you are depositing. And then it only uses a small portion of the source material. So for the thermal evaporation, there is some kind of a limit. You can load a certain amount of the source material per boat. And then if you load too much materials to a boat, after those kind of materials are melted down, it just overflow, and then you eventually lose those kind of a source material. But E-beam evaporation, you do not melt entire source material, but locally melt down the source, and then even you can just move around that kind of a concentrated electron beam. So you can load much more amount of the source materials, and then you can evenly consume that kind of a material. So that's why if you needed to deposit very thick film, E-beam evaporation is kind of a better choice. And then E-beam evaporated film offers kind of much high purity films. So sputtering is another way of the physical vapor deposition. So the basic thing is you may have two electrodes facing each other. So when you apply a bias, electrons moved from one electrode to another. And then as you just flow the inert gas or reaction gas, actually in this case of the sputtering, you normally flow inert gas. So those kind of electrons collide with the neutrals and then just to make an ionization. So these kind of ions are created by this kind of collisions, and then this kind of ions eventually accelerated to the one electrode, and then it just hit the target, and then those kind of target materials just sputtered out and then just moved to the substrate and then forming a film. The RF sputtering is only differences between RF and DC is the way of you are applying the bias, but eventually when you apply the RF bias, actually the polarity of those kind of two electrodes initially keep changing, but there are big differences in mobility between electrons and ions. So ions cannot follow those kind of frequency changes, but electrons can do that. So basically, electrons can see those kind of frequency changes, and at some point, those kind of, even though you just change the bias with the same magnitude, but actually those kind of electrons kind of accumulated to one electrode, and then it just making some kind of a self-bias. So once this kind of self-bias is formed, all the other kind of a mechanism is almost the same as this kind of this sputtering is doing. So just comparing directly with DC and RF sputtering, RF sputtering can do an insulator sputtering, which DC sputtering cannot do that. And then it has a little bit better ionization efficiency, so it can use a little bit low process pressure. That means it can just have a little bit pure. The film would be much purer when you're using an RF sputtering. People use a magnetic field, electromagnetic field. The basic idea to use this kind of electromagnetic field is, and as we discussed at the previous lecture for the etching, basically people want to increase this kind of travel distance of the electron. So by increasing this kind of travel distance of the electrons, it just increases the possibilities of the collision of the electron with the neutrals. So it just simply increases the plasma density. So more numbers of the ions and radicals are available in the plasma. So those kind of more numbers of the ions will eventually contribute to producing more target molecule generation. And this kind of a magnetic field not only applied for the chamber, but also it also applied to this kind of a target as well. So when people put this kind of a permanent magnet on the backside of your target, those kind of secondary electrons just keep hopping based on this kind of magnetic field formed. So this kind of secondary electrons just cause more ionization, and then it just generate more ions population, so it can just increase the sputtering yield. But the problem is, as this kind of magnetic field is kind of fixed, so those kind of target materials are not evenly consumed, but it is kind of consumed with some kind of patterns. So some areas, its consumption is kind of much faster than the others. So that's the kind of disadvantage using this kind of magnetic sputtering. One of the big advantage, just compared with the evaporation, the sputtering is kind of a much more advantageous when you need to deposit alloy or compound materials. What happens is, as we just discussed a couple slides before, evaporation, those kind of a different kind of flux of a target molecule is based on the melting point, melting temperature differences, which cannot be fixed unless you are using two different kind of a power source, can use two different kind of temperature. But sputtering yield, if you have a target which is a compound made of compound A and B, let's say the sputtering yield of the A element is kind of much faster under the same kind of a condition. But then what happens is, during the initial sputtering cycle, this kind of A element sputtered more. So the flux of the A is kind of much higher than B. But after some times passed, what happens is the surface of this kind of target material becomes B rich, since the A element removed much faster than B. So under the same kind of sputtering conditions, what happens is this sputtering yield between A and B becomes 1 to 1, because simply the concentration of the B on the surface of this target is kind of much more. So under the same kind of sputtering conditions, without doing anything, without using any separate power supply, sputtering can deposit much closer stoichiometry of the compound deposition by this. So that's the one of the advantages using the sputter, the evaporation. Reactive sputtering is another kind of advantage. So when you need to using deposit some kind of an oxide or nitride, what happens is instead of, for example, if you want to deposit silicon oxide, instead of you are using silicon oxide target, if you are using a silicon target and then flow oxygen gas, what happens is those kind of an oxygen gas just coat the surface of the silicon, and then because of the surface of the target is kind of coated by the oxygen during the sputtering process, so even though your target is made of very high purity silicon, but what you are depositing is on silicon dioxide. So when you use this kind of a reactive sputtering, good advantage is you can deposit much purer silicon oxide film compared when you are using silicon dioxide target for the sputtering tool. So using this kind of a reactive sputtering, this kind of a sputtering can make a pretty good quality of the oxide film or nitride film. So that's the one of the good advantage out of this kind of sputtering techniques. So just simply compared with the sputtering and evaporation. Sputtering using plasma. So it just sputtered out those kind of target atoms from the target material. So those kind of sputtered target element has a little bit more energy compared to the element evaporated. So this kind of a little bit higher energy makes contribute to better adhesion, and then it also contribute better step coverages, because those kind of atoms has a little bit more kind of energies. So upon those kind of those kind of vapor phase molecules landed on the substrate, it has more energy to hop around on the surface of the substrate. So that is why it can have a much better adhesions and then better step coverage. So that is why the sputtering technique is much more popular for those kind of chip makers, chip making industries. But the problem, even though the sputtering offers a little bit better step coverages, but basically this is a physical vapor deposition. So this kind of physical vapor deposition, those kind of movement of those kind of target molecules, it is kind of very directional. So it always have kind of a filling, kind of a limitation, filling this kind of a nano size of the cavity. So this is the good example. So this black structure is the silicon nano cavity formed on the silicon. So the cavity is it's about 300 nanometer in diameter and then 300 nanometer in depth. So I just deposited silver using sputtering, and then I also do the sample rotation. But as you can see, in the vertical thickness on the flat surface is on about 140 kind of a nanometer. But the lateral side, the thickness is kind of on about 60, and then as we go deeper to the cavity, the thickness of the film is kind of getting thinner and thinner, and especially in this kind of a corner of this cavity, this thickness is only 30 nanometer, which is on about 20% of this kind of vertical thickness. So if our process is kind of designed to fill all this kind of a nano cavity, this kind of a vehicle, this sputtering or evaporation is not a good choice to deposit these materials into this kind of a nano cavity. But this kind of a poor step coverage can be a good advantage. We will discuss about this later. But for filling the cavity, it is not a good method. So what happens if we just continue to deposit film, much thicker film, in the same kind of structure? This is the same kind of silicon nano cavity, and then instead of that kind of this is on about 200 nanometer thick, so which is very closer to the case I just showed you in the previous time. So if we just add about 200 nanometer more kind of film, what happens is instead of further filling these void structures, this kind of films just accumulated in the openings, and then eventually these openings are closed as we deposited more thicker films, and then this void never be able to removed. So that's the biggest problem. One good news for using those kind of physical vapor deposition is you can use a thickness monitor, which is this is the kind of a sensor. So this is the gold, and then this clear disc is single crystalline quartz, and then there is another backside gold. So what happened is using this kind of a two gold electrode, front and back, it's just monitoring the resonant frequency of those kind of a single crystalline quartz. So based on that, it's just monitoring the deposition of the materials on one side of this kind of a crystal. So as more kind of materials kind of deposited on one side of the gold electrode, those kind of resonant frequency of the quartz getting slower and slower. So people just calibrate those kind of frequency changes based on the density of the materials you are depositing. So people can monitoring as small as this much of the deposition rate. So this thickness monitoring is kind of in situ. So that is why you can just precisely control the film thickness when you are using either evaporation or sputtering. So that's the good advantage using that kind of a technique. Nowadays, people are using pulsed laser deposition. The technique is, everything is kind of the same. So like sputtering tool, it has a target. So the sputtering using plasma, and then this kind of a pulsed laser deposition replace the plasma with this kind of a high energetic laser, and then using the laser, it just evaporate the target materials, and then eventually they are deposited on the substrate. So it does not have any kind of plasma induced kind of a damage or those kind of problems. So it is kind of good techniques for some specific application. So we will move on to the chemical vapor deposition. Physical vapor deposition, for the film deposition, we highly rely on those kind of physical reactions. But this kind of chemical vapor deposition is solely depends on chemical reaction of those kind of source materials to the substrate. So there are many variants of the techniques, but we're gonna talking about the atmospheric and low pressure, and then plasma enhanced, and then metal organic CVD today. So this is the general tool configuration. So basically, people use this kind of a tube type or this kind of a barrel type. So since it's using an reaction gas, those kind of a flow rate is kind of pretty important. So if this is the tube, as those kind of reaction gases pass through, it has this kind of a gradient, because there is some kind of a friction between this kind of a gas flow and then the chamber wall. So as the location is kind of closer to the chamber wall, its flow rate is kind of much slower than in the middle. So this is the kind of general reactions what happening on the substrate. So when those kind of reaction gas comes in, there is some kind of a gradient. So those kind of reaction gas diffuse into the substrate and then absorbed, and then it just makes some kind of a chemical reactions, and then the chemical reaction makes some kind of a reaction byproduct, and eventually those kind of reaction byproduct diffuse out and then just merge it to the mainstream of the gas flow and then just removed. So this is the kind of a basic process happening on the substrate using chemical vapor deposition. Depends on the temperature. There are two different kind of reactions. So in a hot temperature, what happens is at hot temperature, those kind of chemical reaction is happening very fast. So those kind of deposition rate is limited by how fast people can deliver those kind of chemical reactions to the surface of the substrate. As the temperature, reaction temperature is kind of getting pretty low, those kind of chemical reaction speed is kind of very slow. In the case of that, those kind of transportation of the reaction gas is not a problem, but those kind of chemical reaction speed at the surface limit the entire growth speed. So depends on this kind of a temperature. There are two different kind of a regime kind of limiting those kind of deposition rate. So atmospheric pressure CVD, actually this is the kind of most kind of a simple type of the reactor. So it does not need any kind of a vacuum pumps. So in atmosphere, it just flow the flowing reaction gas, and then just to heat it up the chamber a very high temperature. In most of the cases, depends on the film you are growing, the temperature can be different, but it normally use close to the 1000 Celsius degree. Since it uses a very high flux of the reaction gas and then very high temperature, what happens is this deposition rate is kind of very fast. And then high deposition rate means high throughput. So this kind of film not only deposited on your substrate, but also the chamber wall. So that is why as those kind of films deposited on the chamber wall very thick, those kind of films get stressed, and then it just generate some kind of particles, and then those kind of particles can put on your samples, so contaminate your samples. So it has a particle contamination problem, and then the uniformity has a problem. So people thought about the technology as a pretty old kind of technology, but interestingly, since it's using a very high temperature, it can grow single crystalline film. So what happens is for the silicon-based solar cell, it needs about 50 micrometer thick layers. In the case of that, people use thin film, which can be deposited by the LPCVD or PCVD. LPCVD's deposition rate is kind of way too slower than APCVD. PCVD does not provide as good quality film as APCVD can do. And then APCVD, since it can just grow this much of the film in pretty short period of time, so people just started to use this kind of APCVD film instead of kind of dicing this kind of big wafers very thin. Actually, the wafer thickness is about 400 to 500 micrometer for about 4-inch wafer in diameter. So to reach this kind of thickness, two approaches. One is just simply slice this kind of thick wafers much thinner, or just depositing this kind of film on a substrate but right now depositing 50 nanometer 50 micrometer thick single crystalline silicon seems like a much more convenient or much more promising process than just slicing those kind of wafers to be seen. Low pressure CVD, this is the kind of a method, kind of making films with a very high purity and then very good step coverages and then excellent uniformity and then quality. Since it's using vacuum, the environment inside of the chambers are well controlled, so that's the reason for making all this kind of a good film deposition. But the disadvantage of this one is it still uses a very high temperature, and then its deposition rate is kind of pretty low. Plasma enhanced chemical vapor deposition, since we are using a plasma, so that is why we are generating a lot of radicals, which is not stable in chemically. So that is why this kind of radicals make those kind of chemical reaction with a very low temperature. Using this kind of PCVD has good advantages this kind of CVD can offer, which is an excellent uniformity, good stack coverages, and then this kind of good advantage out of the CVD techniques. In addition to that, it also offers low deposition temperature and then fast deposition rate. So these additional two features make this kind of plasma enhanced CVD to be the kind of most common method in terms of the film deposition, especially for the microelectronic industries. But disadvantage is since we are using plasma, so we can cause some plasma induced damages, and then the film quality wise, its film quality is kind of much poorer if we directly compare the film deposited by the LPCVD. Meta-organic CVD is a very different version compared with the other three. The major difference is between MOCVD and then the other three CVD is the source material is organometallic vapor. So that is why those kind of bonding of these kind of organic materials, molecules, and then this kind of inorganic molecules, its bonding is kind of very weak. So that is why it only needs very low temperature to deposit those kind of materials. Another kind of a good news is it can just deposit some metals. So it can deposit tungsten and then copper. But this kind of a copper, theoretically possible, but the quality of the copper is kind of much worse than that of the film deposited by the PVD. Since we are using organic source, so this kind of a copper film containing some kind of carbons, so it's kind of electrical resistivity is kind of much higher than that of the film deposited by the PVD method. Thermal oxidation is kind of very similar to the LPCVD, but the major differences between LPCVD and then thermal oxidation is LPCVD, it does not matter what kind of substrate you are using, you can just deposit totally new materials on a substrate. Oxidation, you should consume some of the substrate. So silicon dioxide is one of the example. So when people just grow about 90 nanometer thick silicon dioxide, if then people just consume some of the silicons, to making this kind of film. So the last techniques we're gonna talking about is an electrochemical deposition. So the electrochemical deposition is kind of a wet process. So it use some kind of electrolyte solutions, and then since this needs some kind of a seed layer, so that is why people this is not a popular kind of techniques to use. But the thing is, as we just discussed in the previous slide, to making this kind of metal filled nanocavity structure, this kind of electrochemical deposition is the way we can just deposit this kind of metal layers without making any void structure. So that is why for those kind of peoples, the industry is making those kind of small microchips are interested in using these kind of technologies, because they have multiple layers of kind of devices, and then they just use some kind of interconnect like called as a via, so which is nothing but very small nano cavity, and then they should kind of fill this nano cavity with a metal layer, so they can just connect the transistor built underneath, and then a transistor built in the upper layer. So this is a pretty important kind of a connection. But if there are a void present, those kind of electrical conductivity between these two devices are pretty low, and then it also can fail eventually those kind of entire chip. So in a sense, this kind of electrochemical deposition is kind of pretty promising technology in terms of filling this kind of a nano cavity, which has a high aspect ratio. So this is an example of a system from Applied Materials. So this is an example after filling this kind of a very high aspect ratio of the trenches using this kind of electrochemical deposition. And since there are pros and cons out of this kind of a deposition technique. So con is it does not cover all the materials. So there is some kind of materials you cannot deposit using this technique, and it always need a seed layer deposition. And then morphology control is kind of another kind of problems, but it has a good stat coverage, and then low cost, high throughput, and then it does not making any kind of void structures inside of that nano cavity. So we quickly reviewed all kind of deposition techniques used for making thin films, or mostly for the microelectronic device industries. So let's talk about what kind of a technique is kind of important to making nanostructures. So this is the one of the example we discussed in the previous lecture. So what happening is this kind of masking material is always a problem when you are making this kind of a highly ordered nano element. People wants to have this kind of highly ordered nano element structures, because it not only has a very high surface to volume ratio. If somebody else are developing some kind of a sensor structures, that kind of high surface area to volume ratio is kind of very important. And then if somebody else making solar cell, this kind of regularly, periodically well-ordered nanostructures, making much systematic light scattering, so it can just increase the photo generated carrier creation. So in a sense, people wants to make this kind of a very high ordered nano element. But to make that, the first choice we can do is we can just make these kind of structures by dry etching. So this is the photoresist, and this one is on hard mask. When you use photoresist, what happens is this structure, your dimension is kind of pretty low. Let's say your diameter is on 100 nanometer. But depends on how much you etch away, you should thinking about the etch selectivities between your photoresist and then the materials you're gonna etch away. But if this is an inorganic material, the best chance you can get between inorganic materials versus photoresist, 1-to-1 etch selectivity is the best you can get. Still, no matter what kind of inorganic materials you're gonna etch, it is stronger than photoresist. So, in this kind of a scenario, if this is if you wanted to etch 100 nanometer, and then if you have a 100 nanometer, if then this is on the photoresist is on 1-to-1 ratio, so it is okay. But this etch selectivity is kind of much more, like on 1-to-5. So if you need to have about 500 nanometer height patterns, but still you wanted to have 100 nanometer in diameter. So if you need to have this kind of tall structures, what happens is after the exposure, you need to do the development. But those kind of development process is on wet processing. So as you just to develop and then rinse and then do the final dry, what happens is as those kind of solutions are getting dried up, those kind of capillary force just pulling those kind of tall photoresist patterns together as it just dried, something like that. It's just pulling like this. So in the edges, it can, instead of everything is kind of just aligned independently, it just collapsed, something like this. So it can happen. So in this case of that, we need to use a hard mask, but hard mask is made out of the metal or some kind of a dielectric. So in this case of that, we should use what process? We should use a lift-up process, right? So in this case of that, the poor step coverage is kind of a very big advantage. So if we want to use a metal hard mask, even though sputtering cannot completely fill this trench, but it offers much better step coverage than thermal evaporation. But this kind of a relatively good step coverage is not good to making this kind of a hard mask, because everywhere is kind of connected. So when you remove the photoresist under the metal film, this kind of metal film is kind of disconnected somewhere. So you may have this kind of rabbit ear, and sometimes in this kind of small dimensions, this kind of films kind of just stuck to the substrate. So your kind of a substrate from the top is, instead of the circular, like this kind of very strange structures. So in this kind of things, those kind of a poor step coverage out of the thermal evaporation is a good advantage. We will talk about how to making this kind of undercut structures. Actually, this kind of making undercut structure is kind of getting tougher as you are moving toward to the advanced lithography technology, because in the case of that, those kind of pattern size is kind of much smaller. So you need to have a very precise control of dissolving these kind of underneath layers. But we will talk about that in the later lectures. So in this kind of a specific scenario, this kind of a poor disadvantage out of the thermal evaporation becomes advantage in this kind of specific process.
I have a question.
Mm-hmm.
So the deposit meter is just you spin coating the photoresist, and you deposit a thin metal thing as a hot mask to protect low structure.
Oh, actually, this one is kind of the cartoon itself is kind of a very little bit wrong. So it may just so it seems it should be the correct cartoon is, and this is a substrate, and this one is the photoresist, and then
there's a coming deposit metal thing.
Right, something like this. So when you remove the photoresist, since this film and this film is kind of disconnected, so when this photoresist are removed, this film is kind of removed together, right?
Yeah, right.
And then this one just remained on the substrate,
Okay.
and then this one is kind of removed as well.
Okay.
So in this kind of cartoons, it should have these kind of lines, and then this one could be a photoresist, and this one is a substrate, right? Sorry about that. So if you wanted to use this kind of metal deposition for the lift-up process, this kind of a poor step coverage is kind of a pretty good idea. But somehow you have the same nano cavity, but you need to fill everywhere conformally. In this case of that, what the techniques you need to find is another kind of extreme. So to fill everywhere densely, you should find out 8 techniques which gives you a perfectly conformal coating. So ALD, atomic layer deposition technique is the techniques you can use. Actually, I did not cover this atomic layer deposition techniques today's lecture, even though this is the material deposition technique. But since this technique is kind of so important, so I will use one separate lectures only talking about this atomic layer deposition technique. But for this kind of techniques, it can just conformally coding the aspect ratio, which is bigger than 1 to 2000. So this is the somebody else deposit some film to the aluminum membrane, porous aluminum membrane. So from here to here is the trench. So this opening dimension versus all this kind of a depth is more than 1 to 2000 nanometer. So when people just cut here, here, and here, people just see that measurement of this kind of lateral film thickness, and then the atomic layer deposition offers kind of almost perfect step coverages. So This atomic layer deposition technique is used for many applications in nano device fabrication because of this kind of a good advantage. So this is one of the example. Somebody else making a nano colloid, nanocrystalline solar cell using the quantum dot. So those kind of quantum dot just has this kind of organic layer coated, so it does not aggregate in a kind of as they are dispersed in a solvent. So when they just deposit these quantum dot solutions on a substrate, it's kind of nanostructures almost like this, and then this is the substrate, and then this kind of film. So what happens is when the sunlight coming in to this layer used for the light absorber, it may just generate electrons and holes. But depends on this kind of a length of this kind of a capping molecules. The next thing is those kind of electrons go one direction, and then the holes move to the other directions, and then they just making a contribution, and then just recombine in the other electrode again. If this kind of length of the organic molecule is kind of too long, what happens is it's kind of very hard to jump and then just jump around and then eventually collected to the one electrode. So what people are doing is just to change this kind of very long kind of organic molecules with the shorter version. So to increase the conductivities, in another word, to make this kind of carrier hopping much easier. But still, the problem of this kind of material is they are degraded in environment pretty quickly, because when oxygen see this kind of a quantum dot, it just started to make a reaction with this kind of quantum dot. So the degradation of this kind of, no matter how good performance this kind of a solar cell is, degradation is an issue. So one research group kind of have a good ideas, kind of after they just exchange this kind of organic molecules, they just coat another layer of materials using the ALD. So in this case of that, like this kind of an example, those kind of materials should coat those kind of individual quantum dots conformally. So if those kind of technique does not offer that kind of conformal coatings, even though we just put this kind of a layer, additional layer to protect these cells out of the oxygen, but still it will degrade. So if we can just encapsulate all those kind of film perfectly, we can just prevent from those kind of degradation. But those kind of degree of the degradation is kind of very closely related with how conformally we can coat those kind of each of the quantum dot. So in a sense, this is another kind of example. People can use those kind of ALD techniques to coat this kind of quantum dot material, materials. So in organic film is not the only one people can use. So some people kind of making some kind of biosensor. People are using a lipid layer. So the lipid layer is an organic material. So it is kind of pretty comfortable to the bio molecules. So you can even modify this kind of films, and then even you can just put some kind of a probe molecules to catch some kind of a targeting biomolecules. But in this case of that, people just make some kind of nanopores. Scale by is 10 nanometer in this cartoon. So this pore size is on about 20 nanometer or smaller. This pore originally made out of the inorganic material, so which is not compatible with the biomolecules. So to make this kind of inorganic nanostructures to be much more compatible to the biomolecules, people just, we will talk about this more in the molecular self-assembly lectures. So people just make this kind of nice uniform one single bi-layer, lipid bilayers, and then you can just coat nicely and very uniformly these kind of nanostructures. So this is another kind of example. People can use this kind of very conformal coatings for the nano application, but the technique for this kind of coating is kind of very different from the techniques we discussed in this lecture for those kind of organic, inorganic material deposition. So this is the deposition techniques that I wanted to discuss today. So we talked about the deposition techniques used for inorganic material deposition, like physical vapor deposition, chemical vapor deposition, and electrochemical deposition. Actually, physical vapor deposition techniques also can be used for polymer layer deposition. And then we also talked about the deposition techniques used in the nanotechnology. So next lecture, we're gonna talking about optical lithography techniques used for this nanotechnology. Okay, thank you.